Hi, this is Melanie Fine from Chem and 10, and today we're going to talk about advanced Lewis dot structures. In other words, exceptions to the general octet rule. So let's look at this flowchart. To do Lewis dot structures, we count the number of valence electrons, we distribute the valence electrons around the atom so that everyone has a full octet, which is equal to 8 electrons. That's the general overview. There are problems that happen when we do this. Not all of them can get a full octet. So we have three different types of problems. We have one where there aren't enough electrons to go around. Another one where there are too many electrons, so atom's going to end up having more than 8 electrons, or there's an odd number of electrons. So if everyone's supposed to have 8 electrons in its outermost shell, an odd number of electrons doesn't really work because not everyone can have 8 if you have an odd number. If we don't have enough electrons to go around, remember that hydrogen and helium, by the way, only need 2 electrons to fill their outer shell. So they don't satisfy the octet rule in the sense of 8. They have a full outer shell with 2 electrons. Then we form double and triple bonds. And I put many videos out there to show you how to, if you don't have enough electrons to go around, you can draw double and triple bonds. The other case is if there are too many electrons. Then we look at the central atom. If the central atom is in the 3rd to 7th periods, we can actually have an expanded valence for that central atom, meaning it can have more than 8 electrons. The reason being, once we get to the 3rd period, we're employing the d orbitals. So even though a full s and a full s and a full set of 3p orbitals would hold 8 electrons altogether, with the d orbitals, we can now hold 10 more electrons if necessary. And the third case is if we have an odd number of electrons. To determine where to put the odd number of electrons who doesn't get a full outer shell, an octet, we use formal charge. So let's get started. Let's look at incomplete octets, then we'll look at expanded valence, and then odd numbers of electrons. Let's first look at incomplete octets. Beryllium, boron, and aluminum often have incomplete octets. So we will find examples where the central atom is beryllium, boron, or aluminum, and they will have incomplete octets. For example, here we have beryllium dihydride. Notice that beryllium is surrounded by 2 bonds, or 4 valence electrons, not 8. Here we have boron trifluoride. Each bond is 2 electrons, so overall there are 6 electrons around the boron, so that's an incomplete octet. And aluminum, the same case. Aluminum trihydride has 6 valence electrons. So there are cases with beryllium, boron, and aluminum, you just have to memorize these 3 atoms, that may not have a full octet. Expanded valence. Atoms with d orbitals can be surrounded by more than 8 electrons. So in order to have expanded valence atoms, they have to be atoms that have d orbitals, so they have to be in at least the 3rd period on the periodic table. So if you have an atom that's in the 1st or 2nd period, that atom cannot have an expanded valence. For example, here we have phosphorus pentachloride. Notice that phosphorus is surrounded by 5 bonds. That's 10 electrons, which we would think is in violation of the octet rule, but since phosphorus is in the 3rd period, it can have an expanded valence. And here we have bromine pentafluoride, and bromine is surrounded not only by 5 bonds, which is 10 electrons, but also a lone pair. So it's actually surrounded by 12 electrons. Bromine, not being in the 1st or 2nd periods, can have an expanded valence. And finally, odd numbers of electrons. We want to place the odd electron so that the formal charge is as small as possible and that the most electronegative atom has the most negative formal charge. So bear with me, I'll show you how to calculate formal charge. Formal charge is equal to the number of valence electrons around an atom minus the number of non-bonding electrons minus 1/2 the number of bonding electrons. Here we have carbon dioxide. Carbon dioxide has, we have carbon, which has 4 valence electrons, and we have 2 oxygens. Each oxygen contributes 6 valence electrons for a total of 12 valence electrons. So carbon dioxide altogether has 16 valence electrons. We can draw the Lewis dot structures 2 different ways. Usually you see the second way automatically, but let's say we draw the Lewis dot structure the first way. And by the way, this is not an example of an odd number of electrons, it's just an example of formal charge. So let's calculate the formal charge of the atoms in each of these molecules. Okay, so if we look at the formal charge of carbon, it's calculated as the number of valence electrons it brings to the table, which is 4, minus the number of non-bonding electrons. It has no lone pairs, so it has no non-bonding electrons, minus 1/2 the number of bonding electrons, or as I like to say, minus the number of bonds. Carbon is surrounded by 4 bonds. So 4 minus 0 minus 4 gives us a formal charge for carbon of 0. The oxygen on the left, its formal charge starts with 6, which is the number of valence electrons it brings to the table, minus the number of non-bonding electrons. Oxygen is surrounded by 6 non-bonding electrons, minus the number of bonds, which is minus 1. So the total formal charge for the oxygen on the left is -1. And the oxygen on the right, it also brings 6 valence electrons to the table. We subtract 2 for the 2 electrons that are non-bonding, and we subtract 3 for the 3 bonds, and we get +1. So the total formal charge of carbon dioxide in this case is going to be 0. Let's look at carbon dioxide in this case. Here we have carbon contributing 4 valence electrons, minus the number of non-bonding electrons, which is 0, minus the number of bonds, which is 4, for a total formal charge of 0. The oxygen on the left is going to be identical to the oxygen on the right. It brings 6 valence electrons to the table, minus 4 non-bonding electrons, minus 2 bonds. So that's equal to 0. And the formal charge of the oxygen on the right is the same, it's 0. So again, the total formal charge of the molecule is 0, but notice that every element in this Lewis dot structure on the right has a formal charge of 0. So this is the ideal Lewis dot structure for carbon dioxide. This is not ideal because if we can get the formal charges to be 0, that's what we want. Second of all, if, let's say, we couldn't get the formal charges of each element to be 0, we'd like the most electronegative element to be 0. And in this case, we have, not to be 0, I'm sorry, the most electronegative element to be negative. So in this case, we do have oxygen, which is more electronegative, has a negative formal charge. But the other oxygen has a positive formal charge, and we don't want it to be more positive than carbon because oxygen is more electronegative than carbon. So that's our example of computing formal charge. So let's go back to our odd numbers of electrons. Nitrogen monoxide. Nitrogen contributes 5 valence electrons, and oxygen, as we know, contributes 6. So we have this odd number of electrons, 11. So we have 2 Lewis dot structure possibilities. We either have the odd number of electrons on the nitrogen or the odd number of electrons on the oxygen. To tell which one to use, we're going to calculate formal charge. Starting with the nitrogen, nitrogen brings 5 valence electrons to the table, minus 3 non-bonding electrons, minus 2 bonds is equal to 0. The formal charge of oxygen, oxygen brings 6 valence electrons to the table, minus 4 non-bonding electrons, minus 2 bonds, and that's also 0. So we like this a lot. I can almost already tell that this is the Lewis dot structure we're going to go with, because not only is the entire formal charge of the neutral molecule 0, but the formal charge of each element in the molecule 0. Let's consider the Lewis dot structure on the right. Nitrogen here brings 5 valence electrons to the table, minus 4 non-bonding electrons, minus 2 bonds, for a total formal charge of -1. And oxygen brings 6 valence electrons, minus 3 non-bonding electrons, minus 2 bonds, and that's +1. So the total formal charge is also 0, but oxygen, being more electronegative than nitrogen, should have the more negative formal charge if it has to be non-zero. So we like the Lewis dot structure on the left best, and that would be where we put the odd number of electrons. I hope you enjoyed this video. To get more chemical bonding help and a free gift, go to purplebonding.com. This is Melanie Fine of Chem in 10.